We'll give her 1 minute here. Anybody, before we get started formally, is there any big questions about the assignment? A couple quickly, frequently asked questions. Yes, everyone has to hand it in online. Do not go through the lecture link. Go through your tutorial link. Therefore, your TA has access individually only to your assignments. The whole system will shut down at 4 o'clock on your due date. And since the submission is through the tutorial that you're actually signed up for, I know that dozens and dozens of people went to the wrong tutorial last week. So get that straight. But regardless of what tutorial you might have gone to, because your submission is linked with the tutorial that you're signed up for, if you accidentally go to your tutorial page 2 days late, you'll be late. Okay? And it won't even allow you to upload your assignment. So make sure you have that correct. I anticipate, I'll throw this out there right now, it's the first time we're almost guinea pigging the Turnitin system through Blackboard right now. I'm anticipating massive issues. Only because this happens every time somebody does it the first time. It'll probably be okay. I've put a little instruction in there if you have an issue. I don't want to, I'm sure it'll be fine, but if there are issues, there's some instructions when you submit it on what to do, okay? If there are issues with the computer, that's one thing that's outside, or issues with the system, that's one thing that's certainly outside of your control. And we'll deal with that, no problem. All right, any other questions about the assignment that everyone might be interested in? All right, they're all due this week, right? Starting tomorrow. After, this is the only assignment you're going to submit online. Everything else, there is a drop box on the 5th floor now of the S wing near where the TA offices are. The drop boxes is foolproof, okay? There is a picture of your TA with your tutorial section, when your tutorial actually is, etc., etc. There is an arrow pointing up to the actual slot where you were supposed to put your paper. So the arrow's not pointing down. There's no gray area about which slot you're supposed to put your assignment in, okay? It actually has your TA's picture on it. At 4 p.m. on the due date, after not including this one because this is electronically controlled, but after this one, TAs will be putting pieces of white paper in those slots at 4 p.m. This is our foolproof plan for knowing if you're late or not. If your assignment is on top of the white piece of paper, you're late. Okay? If your assignment is below the white piece of paper, you're fine. If the assignment is in the wrong box, you're late. Okay? So be very, very careful when you put it in the box. Yeah?
What if you move the piece of paper?
What if you move the piece of paper?
Yeah.
How would you move it? It's like a little slot, like a 1/4 inch wide. It could not be moved.
Okay.
Okay, good. You guys want to know why I'm so harsh about this all the time? Is because as soon as I let one person go, then everyone's like, oh, how come that person got to do it? Blah, blah, blah. So I can't play favorites with anybody. And we have to have these really strict rules because there's so many people. Somebody had a question. Oh, that's wrong.
Okay, making sure.
Yeah. What tutorial section are you in? I'll fix that. Pardon? Okay, I'll fix that. Yep, in the back. Okay, the midterm exam, off the top of my head, I'm not supposed to tell anybody yet, but it's either on the 25th or 26th of October, which is either a Friday or a Saturday. It's either a Friday night or a Saturday afternoon. That's all I know about it. So don't shoot the messenger. I'm not supposed to tell you because it's not final yet, but it'll be finalized probably this week. I do not schedule them. Trust me, if I schedule them, it would not be on a Friday night or Saturday afternoon either. But that's the word on the street. I'll let you guys know by next week. Okay, let's move on then. So you have anyways, there's a few more weeks of class until the midterm. And so I'm going to say I might even cut lecture material 1 week short prior to that area, because it's almost like by the time October 25th rolls around, I think it's going to be almost 3/4 of the lecture season over with. And so I'm going to make it more close to a real midterm. I might chop off at least one of the lectures preceding the midterm for how much material you guys actually need to know. And then I have more to test you on when the final exam comes around. Okay, so today I only watched Professor Fulthorpe for like 5 minutes, saying I was wrong on a couple things or something here and there. But I'm not sure exactly. He said start at nitrogen cycle. So I'm going to start here. I think she talked about how we have these systems. And so there's a bunch of biogeochemical cycles that kind of run how the important elements in our Earth system between the lithosphere and the hydrosphere and the atmosphere, how all these things move about into these different, we'll call them reservoirs. All right? And so in this case, certain parts of the lithosphere are a reservoir. And certain parts of the hydrosphere, like rivers or oceans, are different reservoirs. And the atmosphere is a reservoir. And then you have these elements by different chemical processes that may move as a flux between these reservoirs. And so if you ever have to calculate a flux, you have to know the concentration, and you have to know how quickly, like the actual mass movement of, say, air that's going from one place to another. So if you want to know from soil to air, then you have to know how quickly vapor or whatever is carrying that thing is moving from soil to the air, and then you multiply it by the concentration. And that's how they get these flux estimates. And so I think she went through probably exhaustively, somewhat went through the carbon cycle. We'll talk about that in a little bit more detail when we go about global warming. I'm going to talk about nitrogen to start off with, and I think you guys probably got there, but I didn't see. So nitrogen is really the massively abundant, one of the massively abundant elements on Earth. The vast majority of our atmosphere that we all know, 6th most abundant element on Earth. It's a key ingredient in all sorts of living things. So all of your amino acids, aminos are all nitrogen-based functional groups. So there's all sorts of nitrogen in key biological molecules. It's essential for plant growth as a nutrient. It's a macronutrient. But it's actually pretty inert, meaning it's not very reactive. And the massive pools in the atmosphere sitting there not doing that much, to be frank with you. And what we are concerned about normally is the overabundance of nitrogen in the lithosphere and especially in the hydrosphere. We'll talk about that in a second. So this is a glance at the global nitrogen cycle. And what you can see here for the big points are the massive number we have in the atmosphere, right? So 3,870,000,000 times 10 to the 12 grams. So huge amounts of nitrogen in the atmosphere, much lesser amounts, for example, in surface waters, in the oceans, some in soil organic matter and the such. And then there's some key processes moving those things around. In addition to kind of the transfer between the atmosphere and, say, water or the lithosphere and back up, there's a pretty intricate nitrogen cycle, particularly within aquatic ecosystems, and that changes the actual molecular structure that you find nitrogen in. So nitrate, ammonium, ammonia, nitrite, all of these little intermediaries and or different types of ions that plants or animals can or can't use are there at different times in different places, and I'll elaborate on this here. So one of the biggest key processes in the nitrogen cycle is nitrogen fixation. And so like I mentioned, we have this massive pool of nitrogen in the atmosphere, but it's very, very inert, very, very unreactive. And there's actually only a couple of ways that we can pull that nitrogen out of the atmosphere for some sort of usable form. If there was no way to get the nitrogen out of the atmosphere, we would not be able to grow any plants. Nothing would grow at all. We would have we would probably all die because our DNA would have we had no amino acid production. All the nitrogen that we really have in our systems originally came out of the atmosphere and then was converted into some sort of process to bring it into the lithosphere or the hydrosphere. Nitrogen fixation is the big one. Lightning is a relatively minor process by which you can actually fix nitrogen in the lithosphere or in the hydrosphere. The big process is specialized bacteria called nitrogen-fixing bacteria. And so there are these nitrogen-fixing bacteria that live in the kind of root or tuber system mostly of quite specialized plants called legumes, for example. And there's some other plants out there like alder trees, for example, and some willows. They will fix nitrogen in their root. They will harbor these bacteria in their roots. But one of the biggest harborers of these types of bacteria that you would be most familiar with is soybeans. All right, so a lot of legumes, will harbor these types of bacteria in them. And that's one of the reasons, for example, that farmers consistently rotate crops, including soybeans, into their crops every few years. Because by rotating growing corn for a year or two, then wheat, and then bringing soybeans back again, then going back to corn, by having those soybeans every few years, you get those nitrogen-fixing bacteria in the soil that pull the nutrients in, that build up your nutrient supply in the soil that can be used by the other plants for a couple of years in the rotation, and then that gets depleted, so you bring soybeans in again, and it goes around and around. So what happens is these bacteria literally pull the dinitrogen gas out of the atmosphere, form ammonia, and then subsequently that gets mineralized into the soluble ammonium ion, which can be used by all sorts of various organisms. Once you have ammonium, plants actually really like nitrate, which is NO3. So yeah, it's all these things. NH3, ammonia, NH4 plus, ammonium, NO3 minus, nitrate. Then there's this little one, NO2 minus, which is nitrite. NO2 minus you don't see very much. It's not a very dominant molecule whatsoever of nitrogen, but it's one of these intermediary steps. Nitrate and ammonium are the big ones that we're really concerned about. That's why you'll see nitrogen fertilizers and all sorts of other applications through ammonium and nitrogen. And it's like highly regulated because you can make bombs out of it and stuff, right? Nitrogen's, if you get in the right place, you guys look it up on the internet, but don't make any bombs. But every time I have to buy nitric acid, I have to fill out a form in my lab that says I'm not going to make a bomb with it. I'm just going to do science or whatever. And so you have this, which makes this so you have other bacteria, which actually converts that ammonium ion eventually into nitrate, which can be easily taken up by plants as part of their uptake of something stuck in my throat. Uptake of macronutrients. And then, at some point, you need that nitrogen if you're going to have a real cycle between the atmosphere and the surface and then back into the atmosphere. So that's why these things are actually cycles. They're coming in and then something's going on, it's being recycled back. You have a third process called denitrification, which is another set of different bacteria. And these bacteria mostly live in relatively wet areas because they're what we call facultative anaerobes. And a facultative anaerobes means that they're kind of adaptive. They don't have to always be in one type of environment, but anaerobe means that they prefer it when there's not a lot or any oxygen around. And so where you usually get these types of things are in wet environments. So if you wet something up, oxygen will get depleted quite quickly, and then you'll have a nice little environment for these bacteria to live in. So we often see denitrification in these kind of important areas like little swamps and ponds that are around in the pond bottoms, and these kind of places where you actually will see denitrification, and then this reaction, catalyzed really by the bacteria will uptake the nitrate, and if the reaction goes to its end, dinitrogen gas will essentially be excreted back out and will get into the atmosphere. And so that's the cycle. So you have nitrogen fixation, nitrification to convert to NO3, denitrification. Nitrogen fixing, nitrification, denitrification. Nitrogen fixing, denitrification, nitrification, denitrification. But we have done all sorts of things to mess up the cycle. The funny thing is, I'm going to kind of show you guys the cycle, and I'm going to show you how we screw it up. All right? And so the big thing that we've done is get all these great technologies in order to take advantage of the capture of dinitrogen gas for the mass production of fertilizers. And this is called the Haber-Bosch process. And so we have doubled nitrogen fixation within the industrial kind of period of Earth, either through overproduction of the legumes, which is a little bit, but largely through the commercial production of nitrogen-based fertilizers through this Haber-Bosch process. And then we've added all these fertilizers in abundance to what they would ever see normally onto agricultural areas and golf courses and etc. We've also done a pretty good job of increasing a couple of nitrogen-based gases into the atmosphere, including NOx and nitrous oxide, mostly from fossil fuel burning, some animal waste decomposition, and these two things are the source of a couple of pretty serious problems. NOx is one part of some of the industrial-based smog issues you can get. And N2O is a super, super powerful greenhouse gas, like 237 times more potent than CO2, for example, but at much lesser concentrations that you generally see. And N2O is a intermediary, really, of denitrification. So if you have denitrification, you have nitrate, and it's being broken back down into dinitrogen gas. If it doesn't get all the way there, you get quite a bit of emission of N2O gas. And so it's kind of like carbon monoxide is a consequence of incomplete combustion, for example. N2O is a consequence of incomplete denitrification. With a lot more nitrogen in the soil, we've started to see the depletion of certain micronutrients, especially cations or positively charged ions and metals like calcium and potassium. And because these nitrogen fertilizers make them much more mobile and they get flushed out. And we've had some issues with forests in particular where some of these micronutrients are no longer accumulating to an abundance good enough for high yields of forest growth within the forest industry, for example. Acid rain. Now acid rain was huge in the 80s and stuff. And we don't talk about it quite as much because it's gone down quite a bit, but the levels of acid rain have actually kind of just tailed off for the last 20 years. They've kind of stabilized, but they're still not zero. So there's two main acids that form up acid rain. One is sulfuric acid, and we'll talk a little bit about that later in a couple lectures from now. But the other main acid in acid rain is nitric acid. And so some of these nitrogen gases that get released, not dinitrogen gas, but some of these other nitrogen gases like NOx and N2O can be converted within the atmosphere to HNO3, literally. And then that is nitric acid, which is a strong acid and brings the pH of rain down into the 4s and low 5s, for example, which makes quite a big deal for all sorts of issues we'll talk about in a bit. Eutrophication is another one. We talked about, these cows, and you get these algal blooms and these ponds and stuff like that. So nitrogen is one, overabundance of nitrogen-based nutrients is one of the causes of eutrophication, or the overabundance of nutrients and then the overgrowth of algae within aquatic ecosystems. Now, nitrogen in particular is noted for its impact on marine systems. So coastal systems like, Chesapeake Bay and all these estuaries have some big issues. St. Lawrence Bay, all these kind of issues like that. Not so much as a base issue for, say, eutrophication in the freshwater environment, say within the Great Lakes. That's phosphorus mostly, which we'll talk about in a little bit. So most marine systems are limited by nitrogen. Most freshwater systems, from a macronutrient standpoint, are limited by phosphorus availability. So those two nutrients are what's usually pushing eutrophication, but it differs usually depending on whether or not it's a marine or a freshwater environment. One possibly good consequence, maybe, of overabundance of nutrients within the lithosphere and the hydrosphere is that it actually increases plant growth. And so there's some hypotheses that more nutrients within the environment actually make trees and make plants and make algae and whatever else grow more. And if they grow more, then how do they grow? You learned last week, I think, by photosynthesis. And so they grow by photosynthesis. If essentially the nutrients make the photosynthesis work better in the end, or make the overall accumulation of biomass work better, then you're actually taking carbon dioxide out of the atmosphere. And it could be a slight deafening, for example, of the accelerated greenhouse effect. All right, so here's a bit more of an in-depth explanation of eutrophication. So eutrophication is the process of nutrient over-enrichment, which causes algae blooms to come up. And then what happens is these algae blooms die. You get this massive increase of organic matter that floats to the bottom of whatever aquatic ecosystem it might be in. And then the bacteria think, it's like being at the Mandarin or something. You have like tons of food, and so you kind of overindulge on whatever is coming in with these dead algae. And so the bacteria eat massive amounts of algae. As they eat massive amounts of algae, they consume in their metabolism massive amounts of oxygen. And so as the bacteria consuming the algae eat up all the oxygen levels in the water drop. And as the oxygen levels in the water drop, all the fish and all the other aquatic organisms that are in there start to suffer. All right, so it's not like the algae are doing this is a common misnomer. It's not like the algae are doing the consumption of the oxygen that's leading to the eutrophication issues. It's that you get these blooms. When you have the blooms, it's actually not too big of a deal. It's ugly and it can be kind of stinky for a little bit, but you have the blooms. At some point, it's going to get colder, whatever's going to go on, those blooms are going to die, they fall, they get consumed as part of the metabolism. Those bacteria breathe. Oxygen, for example, is part of their metabolism. They take up all the oxygen. Boom, no oxygen levels bomb. And so one of the big examples is in the Gulf of Mexico for this, where there's what they call a pretty extensive dead zone out in the Gulf of Mexico where oxygen levels have been dropping. And if a fish accidentally swims into the dead zone, it's like entering a oxygen-free atmosphere almost. If you were to open a door and there to be no oxygen left in there, you'd either get out quickly or you would die. All right, and so there's these areas in here. What would cause the Gulf of Mexico, off the top of your head, to be a hot spot, we can call it, for this eutrophication issue in a marine environment? Yeah.
Runoff, like nitrogen coming down the Mississippi River.
Perfect. Runoff coming down the Mississippi River. Okay? So this Mississippi River is this huge river, drains like 2/3 of the United States, drains the portions of the United States that have the massive amounts of agriculture in them. So all these areas it starts up where I do my research up in northern Minnesota, almost at the Canadian border, branches out, takes, all of the water comes in from all these areas, eventually drains out one point through the Mississippi, well, branches, it kind of gets braided, but essentially from one point in the Mississippi Delta out into the Gulf of Mexico. And so what happens is all the farms in the vast majority of the continental U.S. that are adding too much nitrogen fertilizer to their farms, that's accumulating. You get a big storm. It starts pushing it into the local streams. Those local streams flow into bigger streams. Those bigger streams flow into the Mississippi River. The Mississippi River flows into the Gulf of Mexico. And you have this massive, it's like essentially just a big pipe system of throwing too much nutrients into the Gulf of Mexico. And so with this massive in-stream of nutrients in the Gulf of Mexico, huge algal blooms die, oxygen consumption, fish, shrimp, whatever, die. And the cycle goes on and on depending on how often these pushes are. Algae are temperature sensitive a little bit, so it depends on what the weather's like, or the climate, I should say. There's a few factors that come in there exactly when these types of things occur. So you get things like this guy gets really sad because you get all these fishermen now that are in the Gulf of Mexico that are having serious, serious livelihood issues because a massive part of the fishing zone is essentially nothing in there. All right. Let's talk a little bit about phosphorus then. So phosphorus, hits a little bit closer to home because it's more freshwater. And say we're a little bit more biased toward freshwater around Toronto. But the phosphorus cycle is, I skipped a slide. I switched these two slides around for what you guys have, by the way. But the the phosphorus cycle is massively different from the nitrogen cycle. But some of its important elements are, it's a key component of all sorts of biological things as well, like DNA, cell membranes. You know all these phospholipids, right? On your cell membranes, you have lots of phosphorus in your body doing lots of specialized things. ATP, right? The P in ATP is phosphorus, phosphate. It's a big limiting nutrient for autotrophic growth, like plants, for example, especially in freshwater ecosystems. The big difference between it and nitrogen is that there's almost no phosphorus whatsoever in the atmosphere. Right? There is very, very, very little ways of getting phosphorus outside of sea spray into the atmosphere. And so its cycle is really mostly just between the lithosphere and the hydrosphere. And it's driven by much more kind of chemical, aquatic reactions, like solubilization, which takes the precipitated phosphorus and brings it into solution, or precipitation, which is the exact opposite and puts it back into some sort of solid form, or assimilation, which is the uptake by plants or the uptake by people and its accumulation within those biological organisms, or decomposition as these biological organisms die and break down and that phosphorus is again released. So if you look at the cycle, we can look at that number way at the top that we had millions and bazillions for nitrogen, and it says atmosphere and there's not even a number beside it. Okay? There's practically nothing. There's a 1 beside the transport of dust and sea spray for the movement of phosphorus. But what you do see, for example, well, where's the big one? The huge store of phosphorus is in the sediment and sedimentary rock. And then there's some pretty big ones in soils and the oceans, for example, and in plants and biota. Now, the main way we get phosphorus is by mining. And so rather than, say, for example, for getting nitrogen-based fertilizers for farms, you have this Haber-Bosch kind of industrial process that we take it out of the atmosphere. For phosphorus, you mine it. And I'll tell you right now, we're actually, nobody brings this up very much, but it says 10,000 for mineable rock. That number is dropping like crazy, like a rock in the air. And that number for mineable rock is going down. And at some point, it's almost as big of an issue as oil. And the fact that if we run out of phosphorus, we are going to have some serious issues trying to grow food, for example. And so I've seen estimates where our easily obtainable, relatively feasibly obtainable phosphorus will run out in 50 years. As short as that. Up to a little bit more. So hard to say, but no one talks about that much. So a lot of it that we're getting is from mineable rock. There are these huge stores way down, you know. The kind of cornucopian viewpoint would be if things got really bad, I guess we could go 50 kilometers beneath the earth to try and get some of this stuff, but not quite that far, but far enough. Be like fracking for agriculture. All right, things that we do to alter the human phosphorus cycle. So lots of mining of phosphorus-bearing rock for fertilizer production. And so if we didn't mine that rock and then make fertilizer and then add it onto farms and the such or golf courses where then it gets rainstorms come in and wash it off and solubilize it and move it towards rivers and etc. And those rivers, rather than emptying into the Mississippi River and emptying into the Gulf of Mexico, they empty into the Don River and they empty into the Grand River and they dump into Lake Erie and Lake Ontario and Lake Superior, and that's where we have, or some inland lakes that you might go fishing on, for example. Wastewater and sewage discharge, pretty big source of phosphorus. Over-fertilization I was just mentioning. Phosphate detergents, so when I was younger, every detergent was mostly, its science of how it works was based on phosphate. And then there was a big push in the 80s to get phosphates out of detergents. So there are some certainly that have phosphate in them, but a lot of the detergents that were used and some that are still used have phosphate, and so you're washing your clothes, you have phosphate in your detergent. Where does that go? Down the drain, goes to the wastewater discharge facility, doesn't get treated that well, discharged into Lake Ontario. Yeah. What does it do? It helps to remove, it actually is one of the it helps with the polarization of the molecules to pull the dirt off of the clothes. And so we have some areas. So for example, you guys maybe back in the 70s and 80s, Lake Erie was dead. I mean dead. So Lake Erie, which is, you know, that flows into Lake Ontario, very shallow, very relatively short residence time, massive amounts of over-fertilization runoff into it in the 70s and 80s and before that accumulated in such large blooms that if you took a radar image, you would see all these lakes and Erie would be bright green, okay, across the entire way. And you'd get these huge algal blooms that would die, and you were having Lake Erie with oxygen levels that were down at or less the entire dead zone of the Gulf of Mexico. And so you would be sitting there one day and everything would be cool. You wake up in the morning and there would be a truckload of dead fish on the beach everywhere. And so it was getting out of hand for a long time. And so that's where some of these regulations came in. I'll give you an example. So have you guys ever heard of the Experimental Lakes Area? I think I've talked about it a couple times. It's been in the news quite a bit. Last little bit. The Experimental Lakes Area is this place up in northern Ontario. I did quite a bit of my PhD and my master's research up there back when. And it's a place where you can go. It seems a little bit crazy in a way, but it's a place where you can go and you can manipulate rather large environments and see how they react to certain environmental perturbations. Everything from, reservoir creation for building dams. If you put the water level up in a certain environment, what happens to greenhouse gases and all these kind of things. So you'd go into a place like that, you'd raise the water table up, and you'd see what happens to all the greenhouse gases. Not something you can carry out with any ease down here in municipal Toronto, for example. But one of the things that they did up there was they took a lake system, and this is really what cut phosphates out of most detergents a long time ago. They took a lake system, they put a curtain across the middle, the same lake system, the same ecology on both halves now, same types of processes going on in those two halves. And they took one half and they just kept tossing detergent in it for a couple of years. Detergent. And then they looked at the effects. And within a relatively short period of time, you could have an aerial photograph. This side's pretty clear. This side's bright green all the way across. Boom. Fish start dying like crazy. It was the evidence that everybody needed to say, yeah. And then they took the phosphate out, and they stopped adding the phosphorus and the detergent and stuff, and those ecosystems started to move back toward what that original one looked like. And so that was the impetus, for example, from a scientific standpoint, that really got people off their butts and really got some of these methods changed for making things so we didn't have so much phosphorus in the environment. It's not fixed, okay? Phosphorus, especially in over-fertilization in agricultural area, is still a massive issue, particularly in Lake Erie, although Lake Erie made a massive comeback in the 90s. And it's actually quite decent. I spent a week on there a few summers ago for family vacation. It was pretty nice, except you have to look across the way, and there's all these nuclear facilities and stuff in Ohio and Michigan that you can actually see. But other than that, it's pretty nice. Yep?
What are we using instead of phosphates now?
It's a good question. My guess is something, I don't know off the top of my head, but something synthetic would be my guess. Some sort of manufactured molecule. Yep? Yeah, there are some sulfates. Yeah, there's like, what's it called? Sulfur. I know. Yeah, there's. I remember looking at it on my my shampoo bottle. There is these sulfates in there for sure. Yeah, that's a good question. It's a particular sulfur molecule that they're having some issues with. I remember now too, and I don't know what the whole deal is. So the phosphate levels in Lake Erie came down quite a bit. You can see them, this blue line being where they kind of had their guideline for where they wanted numbers to come down to. And you can see they've kind of come down. These graphs are terrible. It's really hard to get recent information. It only goes to the 90s, but you can see when they made some of these changes that these numbers came down quite drastically. They're still higher in lots of places than we want them to be, especially in this part over here at the bottom of at the St. Clair River, near the Windsor and such, that we call the Western Basin. It's still quite massively eutrophied on a kind of seasonal basis, and there's still a lot of issues going on there. A lot of the rest of the Lake Erie has, mostly recovered. All right, here's my favorite one. So this is a pretty minor cycle. You remember we were talking about, 10 to those numbers, then you had to times them by 10 to the 15 grams. These numbers you only have to times by 10 to the 6 grams. It's a pretty minor thing, mercury. So you have these pretty minor in quantity. You only need a little bit to get super, super sick, right? And so what we have here that I'll start with are, on the left, the mercury cycle that you would have before people started screwing around with everything. And then on the right, the mercury cycle that we have now with the human influence on things. And what you can see, for the most part, is that the mercury cycle and our impact on the mercury cycle is really quite similar to the same impact we've had on the carbon cycle. So if you remember, presumably Professor Fulthorpe told you that one of the biggest issues with the carbon cycle is that we've literally mined carbon out of the lithosphere in the form of fossil fuels like coal and oil, and then burned it and made this awesome new flux of carbon into the atmosphere as CO2. And so we've taken over the lithosphere practically and started shoving all sorts of it more quickly than the atmosphere can handle into the atmosphere. Same thing with mercury. There's two main sources of mercury, anthropogenically anyways, speaking, to the environment. So from man, anthropogenically. The first one, and the biggest one, is the burning of coal in electrical facilities. And so coal has a little bit of mercury in it. And it's very hard to control when you burn it, because mercury can easily volatilize, meaning it can become a gas very easily. It's very difficult to control that release. And so when you burn coal in an electric power facility, boom, into the atmosphere. So similarly, it's moving from the lithosphere into the atmosphere, mostly through industrial activities. The other one is the mining of mercury for use in gold mining, for example. And that's a pretty ongoing large issue in some developing countries for kind of low scale, what we call artisanal gold mining, where gold and mercury love each other. And if you take a pan and you fill it with liquid mercury and you for prospecting and you run some sediment through it, you will start, the mercury and the gold will react and you'll start to pull gold out of the rock. You can then use it, right, for, to sell it and stuff. And so there's lots of aquatic releases from either the mining of that mercury, which doesn't go on that much anymore, or its actual use. Those are the big ones. There's other ones. Waste incineration is a pretty big one for anthropogenic stuff as well, because there's mercury in lots of stuff. Most of those little button batteries you get have a little drop of mercury in there. Mercury is used in all sorts of industrial stuff all the time because it's heavy, it's liquid, and so it works really well as a switch. If any of you guys have an old thermostat and you want to pull the face off it, there's probably a little glass tube about this big in there full of silver liquid. That's mercury. Okay? And it's nice because you can tip it, and if it tips a little bit, the mercury all runs down, and it's really heavy, turns a switch. And if you tip it a little bit, it all runs down, hits a switch. Better than water. It's way heavier than water, for example. And so used that way quite a bit. There's a lot of old industrial things, and then there's all these natural things that go on, like volcanic eruptions that bring stuff back out and into the atmosphere as well. And so the numbers are a little bit smaller, but it's a similar story to carbon cycle in that because of these anthropogenic emissions and this industrial activity, we've massively increased that number that's in the atmosphere from 1,600 times 10 to the 3 kilograms per year, or kilograms to 5,000, right? Over a period of about 200 years. Now, what's the big deal? What's the big issue? How many of you guys eat fish or seafood? How many of you guys never eat fish or seafood? All right, plug your ears. No big deal for you guys, okay? Mercury accumulation through anything like water, drinking water, playing with thermometers for the most part, all sorts of stuff, not that big of a deal. Okay, don't go and play with thermometers on a regular basis, but no one plays with thermometers enough to make it that big of a deal. Inorganic mercury, which is the quicksilver kind of liquid mercury, is not that what we call bioaccumulative. And so if you accidentally ingested some of it, you would excrete some of it in a relatively short period of time. I wouldn't recommend it. It is poisonous, but it will go through you in relatively small doses and not accumulate over longer time periods. The issue with mercury is that there are some transformations that happen in the environment that make it into an organic metallic molecule called methylmercury, which is highly bioaccumulative. And so by being bioaccumulative, what happens is you don't get rid of it very quickly. And if you continue to ingest it somehow and you don't get rid of it very quickly, it accumulates in your body. So it's like a bank account. The inputs tend to be much quicker than the debits. Okay? And if the inputs are much more quick than its use and its debits out, then you're going to accumulate it over time. So for example, somebody who eats a lot of fish has some risk toward mercury accumulation and having some sort of risk towards some problems potentially in the long term. They very much vary. Most people in Canada, not too big of a deal. But people who eat fish a lot and or eat seafood and fish on a subsistence basis, like First Nations peoples, lots of Polynesian, Asian types of cultures and countries that are seafood-based diets, there are some risks involved, because what happens is in aquatic environments, so in lake bottoms, in wetlands, in ponds, in those kind of areas, the same kind of low oxygen areas where I was talking about denitrification taking over, we have what we call obligate anaerobic bacteria. So they don't like oxygen. They actually can't live in atmospheres where there's oxygen because they're obligate, meaning they're not as adaptable. Those facultative ones, they're kind of adaptable. But the obligate ones, they get exposed to oxygen. It's like you having not having any oxygen at all. And so there's some bacteria in there, and we know now that they're quite diverse. A lot of sulfate-reducing bacteria, but some other ones that are involved. And these bacteria will essentially uptake the mercury that's accumulated through, say, atmospheric deposition, and they will accidentally make methylmercury. And then that methylmercury gets eaten up by some little organism or bacteria, and it gets eaten up by something a little bit bigger, and it gets eaten up by something a little bit bigger, and it gets eaten up by something a little bit bigger in the food chains that we're kind of somewhat familiar with from high school biology and stuff. As it goes up the food chain, these things are just eating massive amounts of these things, and they're bioaccumulating it, and actually what we call biomagnifying those concentrations as you go up each trophic level. So by the time you get up into some of the predatory fish, for example, you have concentrations that are millions of times higher of methylmercury than you would actually see in the environment. So if you looked at, say, a sediment or the water, you might see a few percent of the total mercury that's in that water as this methylated form, which is highly bioaccumulative. But by the time you get up into a pike or a shark or something like that, all of the mercury in that organism is methylmercury. And then you eat that. And so then you eat that organism which has the mercury concentrations which are all of this bioaccumulative form. And then if you eat a lot of it, you bioaccumulate. It does come out of you, but generally the people that are at risk are the ones that eat so much of it they never give themselves time for it to, what we call, depurate out of their system. And so, when I was younger, I actually was in shape and stuff, used to work out, blah, blah, blah. Try and give yourself the protein boost by having 2 or 3 cans of tuna a day because you have no money to buy food. You get kind of twitchy, a little bit aggressive. Everyone thinks you're on steroids. That's acute mercury poisoning. Probably. The similar kind of stuff. Mercury has massive kind of neurological and sometimes subtle neurological influences, including aggression and some attacks on your central nervous system, which can mask themselves. Everyone knows a little bit different accumulation and exposure scenario, but everyone knows Alice in Wonderland and the Mad Hatter, right? Say this Mad Hatter, hyper as hell, running all over the place, crazy, can't think straight for 2 seconds. He is based on a case of acute mercury poisoning and called acute mercosis, because hatters used to use mercury to smooth out felt to make hats, and they were exposed a little bit differently through all the mercury vapors that would come up, and they would essentially breathe in mercury all the time. And so over time, until they figured it out, you had all these crazy hat makers running all over the place, not knowing who they are every 5 minutes because they're being exposed to so much mercury. Question?
As far as the fish eating,
yeah.
is it worse if you're eating more like freshwater fish or?
Very good question. So is it worse if you're eating more freshwater fish or more saltwater fish? I'll give you the end of the answer is saltwater fish are way worse, and big saltwater fish are way worse. The start of the answer is methylmercury levels in the ocean are way less than they are in most freshwater environments, like hundreds of times less. And the big issue there, though, is that the food chains in the ocean are way longer than the food chains in most freshwater aquatic environments. And so there's much more bioaccumulative potential up to those fish that we eat from the ocean than there is in most freshwater environments. So, who are the big culprits? So you're going to eat a lot of tuna, eat the cheap tuna. The cheap tuna are the little light tunas that are like this big. If you go for tuna sushi every night, you're in serious trouble. There was a dude that was at this conference I went to, and he was like the head of Geffen Records or something like that, and he was doing this talk, and he was a really big health nut. He's like, yeah, I just go out for sushi every night, and I work out like crazy and stuff. And all of a sudden, his hair started falling out. He was getting like really nervous all the time, and he couldn't work anymore. And they tested him. He said, I don't know if this is true, but for his hearsay anyways, but they tested him in like New York City somewhere, and like, this is the highest level we've ever seen of mercury in a human being, because he was eating sushi like 2 or 3 times a day. And he's eating these ocean tuna sushi. Have you guys ever seen these like reality TV shows like Tuna Hunters or whatever? I don't know what it's called. Where they go, okay? There's these reality TV shows now, and like there's one I was watching the other day. It was like History Network, or no, National Geographic. It's like Tuna Hunters. How big's a tuna? A tuna is about as big as a shark. The big ones that they sell for like sushi tuna. So they're from, I'd say from here to there, 1,000, 2,000 pounds sometimes. Okay, hundreds and hundreds at least usually for tuna sushi. You know, that light sushi gets this. So that tuna sushi that's huge, they live for a long time, they eat lots of fish, and they bioaccumulate. So therefore, they're way up in the food chain, so they bioaccumulate tons and tons of mercury. So the big ones, if you're going to, listen, fish is good for you. I don't want to scare everybody. And everyone, if you're a guy actually, eat fish like crazy until you get, maybe not 3 or 4 cans of tuna a day. But go ahead and eat fish. Ladies, we got a little bit of issue. If you plan on getting pregnant sometime in the next several years, you can do a massive diffusion of methylmercury through the placenta into babies. And so that can actually be, it's a serious hazard. So if you are planning on getting pregnant anytime in the next few years, cut fish out of your diet for like 6 straight months. And then get pregnant. And then you'll no big deal. I made my wife do this twice. Because it will come out of your system, right, if you don't continue ingesting it. But shark, and you can transfer. So if you eat a lot, you have much more risk of accumulating it over time. And the problem is a baby's like a few pounds, and you're putting an adult-sized dose into them through the placenta. And so that's one of the bigger issues. For the most part, no big deal. Do I eat fish? Yes. Do I eat it every day? No. But I really do like it. And do I eat sushi tuna? Yep. No big deal, right? But lots of omega fatty acids and stuff that are good. You just got to weigh the pros and cons every once in a while. But here's the big bad ones: sushi or tuna, shark, mackerel, whale meats and stuff like that. And actually, whale's not too bad if you probably never eat whale. I'm sure. Me neither. What's that? Yeah, sure. They eat blubber. But it's not, actually, whale's not too bad because they actually they're huge, but they eat way lower on the food chain, right? So it's not so bad. Yeah.
How do they make sure that it's not as, you know how you can get fish oil, substitutes?
Yep.
In grocery stores?
Yep. Yep.
How do they make sure it's not there?
How do they get the fish oil substitutes that are low mercury?
How do they make sure that they aren't?
They don't. Lots of fish oil can actually be a pretty good source of mercury. But those little pills, it's just a little pill, right? So it's not so bad. They're usually from cod and some smaller fish, so it's not nearly as bad. And there are, when you said synthetic ones, there are companies that make them they're synthetically made, so they bypass actually pulling them out of fish, and so there's no mercury in them, or really low levels. There are some things available there. Freshwater fish. Stay away if you're really worried about freshwater fish. Can get up there too, especially the big predatory freshwater fish like pike and walleye or pickerel, things like that are high up on the food chain. Those things accumulate a lot. One of the biggest issues that you see that little panther there on the left drinking the water. He's getting it from eating an eagle or something like that. But that was one of the big things that kicked it off in the United States. Was this? They found this dead panther in the Florida Everglades one time, and he had really high mercury levels. And like, what's going on? But he's way up in the food chain, right? And so these things, eagles, it can get out of the aquatic food chain as well, because there's all sorts of birds and stuff that come in, and mammals that will come in and eat some of those high-end fish. So there's all sorts of kind of ecological issues. Where this really came out was way back in the, I'm going to make a mistake here, the 50s, I want to say, in a place in Japan called Minamata. And so sometimes they refer to acute mucosis as Minamata disease. Minamata is this place in coastal Japan where there was a, what the heck did they make? There's a chemical facility making something else. It starts with an A. I'm drawing a blank right now. But they use mercury as a catalyst in making this chemical. And they this is early on, engineers screw up stuff all the time. That's okay, watch out. They're making this chemical. They're using mercury as a catalyst. The mercury is not supposed to change. On accident, they're actually methylating the mercury like crazy, and then dumping it into Minamata Bay as methyl mercury, huge doses. And then the entire city of Minamata essentially goes out there and eats fish out of Minamata Bay every day for 2/3 of their meals at least. And so massive seafood-based diet with huge inputs of this bioaccumulative mercury species being added into the bay. And it was bad. Very, very bad. I mean, if you want to get grossed out, punch in Minamata Bay on Google Images and see what comes up. Because, I mean, deformed babies, people dying, all sorts. That was the big, big one. And then there was another instance in Iran in the 70s, I think. Huge shipment of wheat from, I think, Mexico over to Iran. They had used mercury-based fumigants. So mercury is really, really good fungicide. No crap, eh? Like you can add something poisonous and it can kill biological stuff, but it's a really good fungicide, and they had this mercury fungicide on the wheat so that it wouldn't get rotten as they were shipping it over to Iran. In the ship, the conditions got kind of musty, I would say, as an understatement, and the mercury fungicide started methylating on the wheat because you got in this condition where there was a lot of oxygen in there. These bacteria started taking over and methylating the mercury that was a fungicide on the wheat. It got there, people took the wheat off, essentially made a loaf of methyl mercury bread and started eating it. And there was some serious, serious issues there too. Those are acute issues, so acute poisoning issues. And that's when they really kind of, things hit the fan. But there's all sorts of literature. It's a little bit controversial at times. But the main issue for most people is chronic, low-level, long-term exposure. And on those conditions, the effects are much more subtle, but there can be some mostly based around the nerve system. I think I covered most of the interesting stuff. Yeah? They're obsessed with fish. Put them on the Environment Canada website that says, Google something relatively approachable to your parents. Is this really good Environment? Environment Canada's got a really good mercury website and explain kind of the basics of stuff and show them that. What kind of fish do you eat? Ocean. See, the problem is 95-ish% of the fish that people eat in the world are marine fish. And marine fish are the ones that really accumulate it. We have a little bit of an extra source in Ontario in particular for freshwater fish, but even some of those are quite high. And so the biggest issue is that, some of these things, they get pretty high for the marine fish. Some farmed fish, like give you an example, salmon, pretty good. Not too big of a deal. You guys want some ones that are pretty good? Salmon. Salmon's really quite good. There's some other small issues. Red snappers, kind of up there sometimes. Depends. It's a marine fish, right? So they're about this big too. Do you have a question?
You're saying marine fish, but my family's from the East Coast, so
Yep.
it's mainly cod, halibut.
Yep.
They're pretty low in food.
Yep. Cod and halibut and stuff, not too bad. It can get up there a little bit. I'll tell you what, every inland lake in Ontario has Ontario issued warning about consuming the fish out of that lake because of mercury. Everyone. And the main, so it'll say, okay, you can take fish from here, but don't eat more than X. And there's a guide, if you look in the Sport Fishing Guide of Ontario, there is a number of how many fish you can eat from every inland lake in Ontario. And it's every inland lake in Ontario, the warnings are because of mercury. And it's all, there's no pipe of mercury coming out in almost any of these. It's all atmospheric deposition from coal-fired power plants and stuff like that. Yep.
I have a question. No methyl. If the formula has great, how come it's ME?
Oh, for just the word methyl.
Oh.
Yeah. Yeah, it's not like some Me is not an element that we're trying to throw in the front. Yeah, it's just it's CH3HG plus is the actual chemical formula if you want. But the we generally shorten it to MEHG it's just a common term for lazy people like me. One other big thing I kind of stepped over I should mention I like to test people on is so there's a recent international agreement to decrease, similar to like the Kyoto Protocol kind of thing for decreasing greenhouse gases, for decreasing the use and therefore emissions of mercury in the environment internationally. And I think it's going to probably, is it going to work? I don't know. Very, very new, because the issue is it's really global. What happens is, the one thing I forgot to mention is the residence time of mercury as a gas. Okay, so you can mercury zero, which is the same as the quicksilver stuff that comes out of thermometers. The crazy thing is that it vaporizes like crazy out of there. Also as Hg0. So both of those are as Hg0. The vapor pressure is such that it kind of evaporates very easily. And so Hg0 is this dominant species that we get in the atmosphere, and its residence time, meaning its average time it stays in the atmosphere for, is between 1 and 2 years. Until some rainfall comes in somewhere and scavenges it up, and then it gets dumped somewhere else mostly through rainfall. All right, just a few processes, we don't have to get into it, but mostly through rainfall in these other environments. Meaning, though, that residence time is so long that the mercury raining on us here could be from Montreal, could be from China. Okay, and the mercury raining down on China could be from China, could be from Montreal, could be from here. And so there's been, what I'm trying to say is there needs to be like this global kind of partnership in reducing emissions. And it's kind of similar to the scenario with global warming in that, Canadians not really are trying to lower their emissions through these technologies and stuff, but then we just bump them up from the oil sands. But trying to do all these emissions controls on different things. The Americans are trying to do these emissions controls on different things, and those numbers come down. But then you have these developing economies, like massively developing economies, like China and India and stuff, that are still going towards these older technologies. I mean, China brings on 3 new coal-fired power plants per day right now. And so it's not, I think it's probably, that was last year, but it's kind of lowered maybe a little bit, but the massive development. And so you're kind of counteracting some lowering of emissions and lowering of sources in certain places and increasing them in others. And so, and it matters because the mercury spreads everywhere. It's in the Arctic, it's in the North Pole, it's in the South Pole, wherever you can. I can take a sample from anybody, anytime, any place, anywhere, and measure mercury in it, no problem. All right, let's have a break. So what we call the base concentrations are way lower in the ocean.
for example, the fishes in the ocean has a higher concentration than the marine freshwater?
Right. So there's this kind of paradox where we have relatively low concentrations in the ocean, but relatively high concentrations in the biota, like the fish. And the issue, how that happens is, even though let's say the differences are, the starting mercury concentration in the ocean might be like 30 picograms per liter on average, or something like that. And in a freshwater environment, it might be 500 picograms per liter or more, 5,000 or more sometimes, okay? So maybe 10, 100 times higher in a freshwater environment than it is in an oceanic kind of environment. The biggest issue is, on average, each trophic level you go up. So let's say you go from algae gets eaten by a benthic organism. Usually that benthic organism has between 5 and 10 times higher concentration than the algae that it ate. And the algae has 5 or 10 times higher concentration than the water that it uptook the mercury from. And it goes 5 or 10, 2 to 10, depends on what's going on as it goes up and up and up. So even though there's maybe 100 times difference between the water concentrations in the marine and the freshwater environment for mercury, the issue is that really is only 2 or 3 trophic level jumps. And there's probably 10. You know what I mean? There's a way more elaborate ecosystem in the ocean than there is in Lake Ontario, for example. And so because of this much more elaborate and long ecosystem, and so these chains are much longer, then there's much more bioaccumulative potential. And so even though it starts small, it goes up, it ends up higher because of the bioaccumulation in the higher numbers of trophic levels. Okay? Let's move on. Last cycle we're going to talk about is totally different and totally abiotic and mostly physical, and it's the rock cycle. Okay, so the rock cycle, so anybody taking AO6 next semester? You like half the course on the rock cycle. Like Nick Giles is a geologist, so we're going to spend like 3 slides on the rock cycle, and then we're going to go on with everything else, and we'll let Professor Giles cover that in AO6. But I like to cover it because it gives you a bit of an idea about the history of the Earth, which is really, and how it works, and which is really important, really, frankly, for how everything else kind of goes on after it. And so, in the rock cycle, you have rocks essentially made by compressing matter, okay? And compressing matter and cementing matter together, there's all these different things that form rocks. But depending on how those things really occur, you get different types of rocks. And you actually get some rocks that become other types of rocks. All right? So a limestone might be a limestone for 1 billion years, and then it gets changed into a marble that you might want to put on your floor of your house if you're super rich or something, okay? And so these rocks actually change back and forth depending on what's going on. So there's 3 kind of ways to make rocks. Let's start with sedimentary rocks. We have lots of sedimentary rock in Ontario, for example. Sedimentary rock is usually rock where you have, say, an old lake or ocean basin from a bazillion years ago, okay? Billions of years ago, we're in the bottom right now of a massive ocean, if you can think back that far. And so why is it so flat around here? It's because go in the bottom of any lake or any ocean, ocean not so much, go in the bottom of any big lake, what's it look like? It's friggin' flat, right? Okay? We were the bottom of this big ocean, massive kind of lake system billions of years ago. And in those systems, you have sediment and particles and dust and algae and whatever else that would be in there, and that will settle down to the bottom of that system, and seashells and escargot and whatever else that it might actually be, actually settle down to the bottom of this system and form these layers over time. And with even more and more time, those layers start cementing themselves together. the ocean drains off somewhere. So, you know, the levee breaks, the ocean drains off, everything dries out, things compress, and that rock kind of compresses itself together, and those sediment layers start to compress themselves together. And then a big glacier might come through and crack it in half, and then we have something left like the Niagara Escarpment, for example. So super flat plateau, been shaved through by a glacier. If you go look at anywhere in the Niagara Escarpment through Hamilton, just almost any direction from here, you can just see layers. All right, and those are layers of dust and seashells, and you can see seashells and stuff in there actually. And a lot of it's calcium carbonate, and so a lot of it's this oceanic kind of stuff that seashells and stuff is made out of, and that's where its underlying kind of chemistry comes from. And so that's how you get sedimentary rock. And now sedimentary rock, if you put lots of heat and pressure on it, so way deep down the earth, lots of magma and stuff, lots of mass, and you're pushing things together, you will start to change the molecular structure of that rock, and you'll start to push those layers together so strongly that you can't see them anymore, and things start to crystallize, and you have all sorts of these crazy reactions go on, and it ends up being another rock. And if you do that to limestone like we have in the Niagara Escarpment, it becomes marble over a long, long period of time. And if you then take that rock and you melt it, it gets pushed in deeper in the earth, or some volcanic magma track meets up with it and melts that rock, and that rock then gets, say, spewed up onto the surface or pushed somewhere else where it's a little bit more cool. And so you've essentially literally melted that rock and then put it somewhere where it could cool down and then reform as a rock. We call those rocks igneous rocks. So three main types of rocks: sedimentary, metamorphic, and igneous. Sedimentary from this long-term kind of settling of layers out. Metamorphic from anything that was heated up and pushed together but not melted and then changed into something else. And then igneous rocks from actually having those rocks melt at such high temperatures and then cooling down. So you have like igneous rocks like granite or something that you like to put on your kitchen countertops, for example. So where's all this heat and pressure and stuff come from? Well, if you took a cut through the earth, this is generally what it looks like. We have this little wee layer at the top called the crust. But starting in the middle, you get this really dense iron core, which is actually solid at its middle, and then is surrounded by molten iron. Beyond that, you have the upper mantle, which is also sometimes called the asthenosphere. This is kind of softer rock. It's kind of malleable. It's hot, super hot that it's just kind of rubbery almost. Yep.
Is there actually like defined borders of each section, or do they
well, no one's been there to check it, but you can see it through geophysics and stuff, seismology stuff, and you can shoot different things, radiative waves into it, and you can see it go boom, because there's massive density differences, things like that. So that's mostly where this knowledge comes from. Yeah. So near its molten point, it's almost melting. It's kind of rubbery. All right. Think if you took something and left it on your dashboard during the summertime, and it got all kind of movable. All right. And then over that, we have the lithosphere, which is made up of the crust and below the crust. And you have kind of this lithosphere that kind of floats on top of the mantle. And so this lithosphere kind of floats on top of the mantle and actually moves around a little bit, extremely slowly. I'd like to go like this, but this would take like 1,000 years. All right, to go that far. But it goes that's like, your lifetime's like this. All right? And so extremely small. But if you took your lifetime and went and times that by knowing that things have been around for billions of years, that can be from here to across the Earth practically, right? If you times it out by enough time. And so these time scales are very, very long. So to think of the lithosphere and the crust on top of the mantle, kind of the best analogy I've ever heard is if you took an orange, okay, and if you took the orange and pretended the middle part of the orange was kind of movable a little bit, and you peeled it off in chunks, okay, took the peel of the orange off in chunks, and then took those chunks and stuck it back on top of the orange, so you'd have these plates that are essentially on top. That's really what our outer crust is like. It's like more like these plates, and it looks something like this. So these are the orange peel pieces that kind of make up our crust. And so all of these plates are out there, and they're actually moving around constantly. So the plates are either moving away from each other, they're either moving into each, and then if a plate's moving away from one over here, it's probably moving into another over there, or they're moving sideways to one another. Regardless, these plates are all moving very, very slowly, but very, very slowly over very, very long periods of time. That's why, I mean, if you've ever seen like Pangea and stuff, and these things where, you know, a lot of the terrestrial part of the Earth, where Africa is in comparison to North America, was totally different 1 billion years ago. And totally different again 2 billion years ago. So these things are constantly moving around. Now, where you have this kind of triangles, okay, those are called convergent boundaries. And so those are where the plates are actually moving toward one another. And I'll show this in a little bit more detail in a second. But think about where all these, most of these convergent boundaries are. One of the best examples is up there in and around India, for example, right? And Nepal and all that kind of area. There's a big convergent boundary up there. If you have two big orange peels of rock and they're running into each other over relatively long periods of time, what's going to happen if they run into each other on top of the Earth? Well, not on top of the ocean necessarily, but a couple things can happen. Usually on Earth, they run into each other and they crush each other up, okay? And they make a big pile of rock. We call those mountains. Okay, so that's how you make a mountain. So if you think about the really big mountain ranges on Earth, it's where these boundaries are coming to each other over long periods of time, pushing up and actually making these big elevations. So we have the Himalayas. We have the western seaboard through North America and South America, for example. So the Andes and the Rockies and all those kind of things. Okay? Where these are really big, these things used to be different places. Where they're really big, it's because they're relatively new in a geological standpoint. And so big, tall mountains are ones that are actually still growing. So some of the Himalayas are still growing. It's still moving toward each other, and they're getting bigger over time. And it's just a race between getting pushed together and eroding. Whereas we have other places where mountains are very old, like the Appalachian Mountains in the eastern part of Canada and the United States. Those used to be as big as the Himalayas at one point. But over billions of years, they've eroded away into these more roundish kind of hills. All right? One example. Divergent boundaries. So we have these divergent boundaries, which are kind of like these yellow lines with the red borders, and they're pulling away from one another. And where they're pulling away from one another, I'll show this in a little bit more detail in a minute. You're actually getting usually you're getting some sort of magma or volcanic activity coming up underneath, and you make these rifts. So these big trenches, for example. And so you can see these rifts and ridges. So you get this kind of valley and then these ridges where the magma comes up and forms these ridges. And one of the big ones is Mid-Atlantic Ridge, which runs down through the middle of the Atlantic. And then you have, thirdly, these transform boundaries where the plates aren't crashing into each other as much. They're not pulling away from each other as much, but they're moving like this. They're kind of rubbing up against each other, sideways. And you can see some big ones, for example, like the San Andreas Fault. This is where you get them kind of moving, and they're just moving a little bit, then they go crack like that. That's called an earthquake. All right? And so you have how these things move against one another. You get a lot of the geological hazards that we're familiar with, including earthquakes, or geological hazards or phenomena, mountains, volcanoes. All of these things depend on how these plates move together, move apart, or move sideways to one another. Yep. A tsunami is a crack, is a submergent. I'll show you a tsunami. I won't show you a tsunami, but I was trying to show you a tsunami. See the convergent plate boundary on the sea? Okay. So in a convergent plate boundary, you can have, or any kind of convergent boundary, two things can happen. The plates coming together, you're either going to subduct. That usually happens in the ocean. So you have a less dense and it subducts. And you get a massive change in the elevation of the ocean. So you either crash together and it comes up and you get an elevation change, but you usually get a subduction and a massive decrease in the elevation change. Now if you took any water and you took the bottom and you went like that real quick of a tank of water, you'd make a huge wave. And that's a tsunami. So really quick change in the bottom boundary of the ocean will produce a big wave, and then the currents take it into the shore. So these are some examples of convergent plate boundaries. Divergent, I'm sorry. So you see them taking apart. They're moving apart. You get this rift in the middle where magma's coming up and forming these ridges on the side. The strike-slip fault that you see on these transform boundaries that are moving against or sideways toward one another. And then two types of convergent boundaries. C, the first one on the left of C, which you usually see in the ocean. And you see that going down. This is how, say, for example, Japan was made. This big volcanic kind of ring of island in the eastern part of Asia. The plate boundary is not exactly where Japan is, but you can see what happens is it subducts. You get this magmatic activity and these volcanoes that actually form a bit of a ring or a bit of a line beyond that. And that's, for example, how the island of Japan was made. There was actually an island that just popped out of nowhere in Pakistan last week. I don't know if you guys heard of that. I'm not sure. I think that was probably some sort of similar thing. And then the final one, which is where they come together, usually on the continental kind of areas, crash up against one another and make mountains. And so as an example, like these tectonics really control what you see for hazards. And we have this kind of area here, which is called the Ring of Fire. So you can see, I'm going to go back and forth here a little bit. You can see these are all massive volcanic activity areas. So Mount St. Helens, Krakatoa, Tambora, all of these areas have led to huge volcanic eruptions in the last couple years of history. Now, if you kind of blink your left eye, take a quick snapshot of this picture, and think about it for a second, and then we go back to this one. It's this area here on the left-hand side of this one, meeting the area on the right-hand side of the map there. So you get this kind of ring, and you end up with this across the Pacific Ocean. It's called the Ring of Fire, and you have this massive area of volcanic activity. Okay, let's take a breath. I'm going to try and get into make a couple of points so we don't get too far behind on the next topic. Okay, energy. We're going to talk about energy for a little bit, and then we're going to get into water so that I can give you some background for the next assignment that you're going to have to kind of get into for school, which is going to focus a little bit on farting around with numbers to solve some water-based problems, okay, for the next assignment. Now, so we're going to not really talk too much about the water cycle until next week, but I want to talk about some of the basics of energy at a physical level a little bit, so real scientific level here. Okay, sounds similar, but people have some misnomers, and I'm going to try and solve some of these. Okay, a substance gets warm because it accumulates energy. Okay? There's no different types of energy. There's no warm energy. There's no cold energy. There's not these kind of different things that you don't get cold because you're accumulating cold, although it feels like that when you're out in the winter. You're actually getting cold because you're losing all your heat energy. All right? So we need to kind of get our mind around that a little bit. So you get a warm substance warm because it holds more energy than a cold substance. And if a warm substance becomes cooler, it's because energy is leaving that substance. If Earth were in a true steady state, all of the incoming energy in a year would equal the outgoing energy in a year, and the change in temperature over that year, from year to year, would be 0. It's not right now. It's going up because we've done some stuff with greenhouse gases, for example, that are making us accumulate slightly more energy year over year generally. So if this is not true, then the Earth will either warm up or cool down. And the Earth's climate is all about energy fluxes and essentially the balance between incoming and outgoing energy. And a big thing to remember is that energy cannot be created or destroyed. It's just transferred around. All right? Remember those things. Now, remember we talked about systems. We had open systems and we had closed systems. Now, Earth's really a closed system, but any closed system is still open to energy. Okay? And in here, our big open part is that we're open to energy coming in from the sun, which we call incoming solar radiation, or insolation, not the insulation you put in your house. Okay? Slightly different word. Insolation is incoming solar radiation, which is different from insulation, which increases the R factor of your home. Now, insolation, because it's coming from a very hot source, the sun, is called shortwave radiation, because I'll show a little physical equation in a minute. But the wave, the length of the wave of radiation is inversely related to temperature. So the hotter the source of energy, the shorter the wave radiation is. So shortwave radiation inputs include some words you've heard before, like UV and infrared radiation and visible light. So between insolation and the Earth's tilt, so it's tilted, I'll show you in a minute a little bit, and it rotates, it turns around, these things, so the incoming energy, our tilt, and us turning around, and then us going around the sun, are what affect our daily and seasonal and annual patterns of day length, climate, energy inputs, all of these kind of things. Right? So it's we're colder in the winter because we have less insulation, because we're tilted away from the sun, and we don't have as much daylight. All right? Those are the big reasons why it gets cold. And so we have an inverse balance relationship where we are losing more energy than we have coming in. And so it gets cold, winter, snows, etc. When that gets turned around, the balance turns the other way, things get warmer, we get summer. So from a tilt and rotation standpoint, this is what it looks like. So the Earth's tilted on its axis by 23.5 degrees. It's actually kind of substantial. Right? It's not, Earth does not stand up, sun's not here, and Earth's not straight up here on its long axis like this. It's like this. And then it goes around. It's rotating, and then it goes around. And so because it has this tilt, it has a pretty big impact on variations throughout the year, as long as you don't live at the equator. So if you live at the equator, things don't change that much depending on the year, because you're pretty much always in the same position regardless of the tilt. But if you live at the North Pole or in the Arctic Circle, for example, that tilt makes an enormous impact. So let's look at December solstice. What's December solstice? 21st of December, first day of winter. Okay? Longest day of the year for us. Okay, longest night of the year for us, shortest day of the year. For us in the northern hemisphere, the longest day of the year, if we're so northern hemispheric central, it's actually the longest day of the year for people who live in the southern hemisphere. And so it's also the start of winter, and if you can look at that North Pole kind of area for the December solstice on the right-hand side, and think about in your mind about rotating that Earth one time every 24 hours. So it's going around and around on that axis. What never happens if you turn around on that axis? Even if you turn on the axis in that position and tilt it away from the sun, you're never going to see sunlight at the North Pole in the winter. Okay? So this is why it's dark 24/7 during the winter at the North Pole. Literally, the Earth is pointed away. So if you're having something like this and you're going like this, you're never going to, have whatever's being shot at you from over here hit you on this part, but it might hit you in the bum, which is the southern hemisphere, for example. Okay? Think of it that way. Whereas you turn, you go the other way, you hit the June solstice, which is the first day of summer, the longest day of the year and the shortest night of the year that we have in the northern hemisphere. And then the very opposite, what you see, think about that North Pole and it rotating around. It's always pointed at the sun during the entire day. So there's 24 hours of sunlight at the North Pole and everywhere above the Arctic Circle for all day during June 21st. And it gets slightly, it's pretty much light for quite a while, ever so slightly less as you move toward the December solstice. And then you have the equinoxes in March and September, which are the start of spring and the start of fall, respectively. And during these equinoxes, you have essentially equal time between day and night. Now, these have big impacts for radiation. So, for example, the North Pole is super cold because it spends months and months not even pointing toward the sun, so having no insulation at all. And it really can't get over that deficit even when it comes around, the sun's pointing at it the whole time. Because you can still see, for example, at the equator, the Earth's bulbous, right? It's like the sphere. So at the equator, you can still see that area at the equator is way closer to the sun than is the North Pole, even though the North Pole is light the whole time. But the equator turns dark because that fat part comes around on the other side and you get darkness, right? But it's way further away still. All right, good. So this is how we get our night and day. We just turn, right? This is how we get our seasons and stuff, is because we go around the Earth. And it depends on the tilt and how close that tilt makes us. So, for example, in the North Hemisphere, you can kind of see Canada there. We're closer in the June solstice than we are in the December solstice. All right, so remember that tilt, 23.5. All right, two little things. Then I got you for 6 minutes. Don't look at that clock. It's wrong. So I talked about the shortwave radiation coming from the sun. Then we have long-wave radiation. So I'll let the cat out of the bag. Shortwave radiation comes from the sun when we're talking about the Earth's energy balance. Long-wave radiation comes from the Earth itself. Okay? So shortwave from the sun, long-wave from us. You're emitting long-wave, you're emitting long-wave. Everyone's emitting long-wave radiation. I'm emitting long-wave radiation right now in relation to how hot I am. Okay? Not in that sense, don't worry. My temperature is related to my emission of radiation. The sun's temperature is related to its emission of radiation. The Earth's temperature is related to its emission of radiation. And so this short-wave, long-wave thing is actually just a relative term. All right? The sun is way hotter than the Earth, so its radiation is a shorter wave. And so we call it shortwave. It's not as it's kind of defined, but for us, we don't have to worry about it, okay? It's a shorter wave. The Earth, on average, is like 10 degrees, 12 degrees Celsius, way cooler, and so it's a longer wave radiation that it would emit. And this is how you define that wave. So all light, UV radiation, radio waves. I mean, you get a radio wave can be kilometers between that hill and crest, for example. And you get this shortwave radiation, which has nanometers, like really, really short distances between those peaks and troughs. And that's how energy comes in these waves, all right? And if you want to think about the actual wavelength, then there's a little tool here called Wien's displacement law, which states that the wavelength at which maximum radiation occurs is inversely related to surface temperature, and you can calculate it using this equation. So it's a simple equation, 2,897 over the temperature in degrees Kelvin. That's important. Okay? So degrees Kelvin. Now how do you get degrees Kelvin? 0 degrees Celsius is 273.15 degrees Kelvin, and everything else is 1 to 1. All right? 0 degrees Kelvin is what we call absolute zero. Everything freezes. That's what it's based on, the Kelvin degree scale. Everything freezes at 0 Kelvin in the world. So we use it quite often from the scientific standpoint. So if you took this, and so if you have a hotter emission source like the sun, which is like 6,000 degrees Kelvin, you're going to end up with a wavelength of maximum energy, maximum displacement at, roughly half a nanometer. Whereas the Earth is something like, say, 10 degrees Celsius, you're going to get a maximum emission at 10 nanometers. Okay, so it'd be like 2,897 divided by about 290. And so you're going to have somewhere in around 10. So there's one shorter than the other one. Now, I should say, this is one wavelength that you get with this equation. Be very careful about what the equation says. It's the wavelength of maximum emission. So the wavelength at which the most amount of emission occurs. Everything emits according to a spectrum. Okay? So there's some emission at different wavelengths, but the emission at which most of that radiation comes is that 1 point. Hold on, I got 2 minutes. Settle down. And this is how it works out. So for example, that 5, what did I say? I think I screwed up the units there. Hold on. Sorry, you get it in microns, not nanometers. I think I said nanometers. Micrometers, which is a millionth of a meter. A nanometer is a billionth of a meter. Okay? And so in a micrometer, so you get, say, we said 0.5 micrometers, which is 500 nanometers. So right down there, in the middle of the visible wavelength-ish, is where, down near looking blue, is where we see quite a bit of sunlight. And then, whereas we're more giving off infrared radiation from the Earth as a slightly longer wavelength. And you can see all the radio wavelengths are down there at, hundreds to thousands of meters long between their peaks and troughs. So as an example, a couple of temperatures that you could look at as an example. Okay, we'll talk about the actual flux, how much energy comes off, and then how this relates to water moving around the environment next week. Remember to hand in your assignments online.